For our last example today, we want to review some equilibrium chemistry related to the solubility of ionic compounds and evaluate the KSP of a water-insoluble ionic compound. This is going to relate directly to our consideration of how dissolved CO2 is impacting coral reef health on Friday. And the question we want to answer in this example deals with an ionic compound, gypsum, calcium sulfate, which is similar in many respects to calcium carbonate, limestone. We want to know what is the solubility of calcium sulfate in grams per liter in a neutral aqueous solution. This is going to be strictly a review of ionic compound solubility related to general chemistry. You might remember in early general chemistry, according to your solubility rules, we would say that calcium sulfate is likely a water-insoluble ionic compound. Later on in Gen Chem, you learn to deal with solubility quantitatively, and you could say what the concentration of calcium ion would be if we had a saturated solution of calcium sulfate in water using an ice table. What we would need to do first is write a dissolution reaction for the ionic compound. 1 mole of calcium carbonate, solid, breaks apart to give us a mole of calcium 2+ ion and a mole of sulfate ion floating in water. The KSP expression is, as ever, products over reactants. However, the calcium carbonate itself does not appear in the KSP because pure solids and pure liquids are omitted from equilibrium constants because they have no concentration. So the concentration of calcium 2+ times the calcium of sulfate, concentration of sulfate, is our KSP expression. From the table in our book, we can find that the KSP at 25 degrees Celsius for this ionic compound is 3 × 10⁻⁵. So it has very borderline water solubility. Using our ice table, we'd first cross out the column relating to calcium carbonate because calcium carbonate does not appear in the equilibrium constant. The initial concentrations of the products, calcium 2+ and sulfate, are 0. The change would be +X and +X because we make 1 mole of each ion as the ionic compound dissolves. And so our equilibrium concentration of calcium and sulfate would be X and X. So we could then find our equilibrium calcium concentration by taking the square root of the KSP. Now, where we're introducing a little bit of vocabulary that's different from what you were maybe exposed to in general chemistry, is we would refer to that calcium concentration as the molar solubility of calcium sulfate in neutral water, which we abbreviate capital S. So the solubility, the molar solubility of calcium sulfate is equal to the square root of the KSP, which is equal to the equilibrium calcium concentration, 5.48 × 10⁻³ molar. However, in this case, the solubility we're asked to give is not the molar solubility, but the solubility in grams per liter. So we need to relate the molar solubility of calcium sulfate to the amount of calcium sulfate that would dissolve in water using the molar mass of the calcium sulfate. So we can do that this way. The calcium concentration is equal to 5.48 × 10⁻³ moles of calcium per liter. We have 1 mole of calcium sulfate that started out for every mole of calcium 2+ that dissolves. If we multiply by the molar mass of calcium sulfate, we would then know the solubility of calcium sulfate in grams per liter. So we convert the molar solubility to the solubility in grams per liter by essentially taking the stoichiometry of the chemical compound into account and multiplying by the molar mass. 5.48 × 10⁻³ times 136.14 grams of calcium sulfate gives us a mass solubility of calcium sulfate of 0.77 grams per liter. We're going to pick up on Friday with a similar example where we evaluate the solubility of the coral exoskeleton as limestone in water, and then we're going to introduce the idea of coupled equilibria and how increased CO2 dissolving into the ocean water is going to make the coral exoskeleton more soluble. How much more soluble? We can say with pretty good certainty by considering equilibrium chemistry. That discussion will carry us into Monday. I'll see you back here on Friday.